A very good afternoon to everyone. This is V S Rajashekhar representing Indian Institute of Science, Bangalore. I am currently a PhD student at IIT Kanpur. This work was done by me during my tenure at IIC Bangalore. I am guided by Professor Rajashekhar V S and R.K. Selvakumar. The title of the presentation is Optimal Kinematic Design of a Robotic Lizard using 4-bar and 5-bar mechanisms. The presentation overview is as follows. I'll be dealing about the overview, mechanism design, determining the lengths of the various links in the mechanism, that is dimensional synthesis based on performance chart, and then I'll be dealing with the kinematic analysis of the mechanism, followed by the singularity identification, gate analysis, and then I'll be dealing about the experiments and the concluding remarks. In this work, the aim of the work is to mimic a common house, common gecko which is in the house. That is, lizards we find everywhere in the house. So our aim is to mimic that gecko, and so we are working on this project. And this is made up of 4 5-bar mechanisms which form the body of the robo, and 4 4-bar mechanisms which form the leg of the robo. The dimensional synthesis of the mechanism is done, followed by the forward and inverse and kinematics, for which the configuration space singularities are done, and the gate analysis, followed by the experimental results are shown. This is the overview of the presentation, and this is a common house gecko, and this is the body of the CAD model of the robo which we made. The yellow dots represent the active joints. That is controlled using rotary actuators. That is, we use servo motors, and the blue rectangles on the body of the gecko means that there is a prismatic joint at that point. It is a RRPRR. RR means revolute, prismatic, revolute. So it actually mimics the lizard in a very good way if we design in this manner. And the leg is like this. It is a 4-bar mechanism with the leg portion extended in the forward direction, and a spring is connected to the body mechanism so that when the body moves, the leg also moves. This is the overview of the robotic lizard. There are 2 subsystems. The one shown in orange is the body. The one shown in the green are the legs, and the one in blue is the chassis. You can see a tension spring which connects the body and the leg, which is present at the 4 corners of the mechanism. This is the CAD model which you can see in figure A, and this is the 3D printed model which you can see at the bottom. This is the kinematic description of the robotic head and tail. So these parameters are useful when framing the kinematic equations. And this is for the side body. The link which is in green in color is the active link. It is positioned at 90 degrees. The L shape is, the angle between the L is 90 degrees, so that it can visually be appealing when the lizard is modeled. So this is the side, left and the right body of the robotic lizard. And this is the leg of the robotic lizard. And parameter design space, we take 3 parameters, and we measure the biological lizard's head portion, and we assign the link lengths to be R1, R2 and R3 as follows given in equations 1, 2 and 3. And then we create a dimensional factor D which adds up to 0.9, and then we form non-dimensional parameters R1, R2 and R3, and they all add up to 0.9. And then the parameter design space is in such a way that the 2 links which are on the half of the symmetry ranges between 0 to 0.9, and the other R3 ranges between 0 to 0.45. And this is the theoretical workspace of the robotic lizard, head portion alone, the 5-bar mechanism. There are basically 4 circles, and within the circle you can see in this figure, within the circle the workspace is plotted. Then there is a concept called as maximum inscribable circle. That is the area inside which the robo actually moves its head or the tail. So this is the marked in red color circle where it is shown in this figure. Then there is a parameter called as local conditioning index in kinematics, which is as follows. Here the Jacobian matrix is taken and the inverse of it is formed, which is multiplied by the Euclidean norm of the Jacobian matrix, and we get the kappa value. And what happens is the local conditioning index is nothing but the inverse of the kappa. And here is the maximum, this is the LCA, local conditioning index. It ranges between 0.1 to 0.7. If it is high, it means that it can easily access that area. If it is low, it means that it is very difficult to access in that region. So this circle is created, this figure is created considering all the 4 5-bar mechanisms. This is the, coming back to the dimension synthesis, this we use 2 servo motors, which is the limitation, where the distance between the 2 centers of the servo motor is minimum, it has to be 20 mm, and we kept that, and we obtained the other parameters to be 30 mm and 50 mm. So the link length of other linkages, links in the mechanism is as follows in the table. So the kinematic analysis of the robotic lizard is as follows. We first find the inverse position analysis, for which we use the geometric method. It is shown in equations 20 and 21. And then we go for the forward position analysis, which is done using the vector loop method. The vector equation is written in 22, and it is written in the scalar form in 23 and 24. Similarly, it is done for other 4-bar mechanisms and 5-bar mechanisms, which is presented actually in the paper. And we are connecting these 2 subsystems together. The subsystem happens to be like this. Here the head 5, you can see in the top right corner, the head 5-bar mechanism is got, and the angles are fed to the left leg and the right leg in the 4-bar mechanism. Then the tail 5-bar mechanism values are obtained, and it is fed to the back leg, left leg, and the back right leg. And then the other 2 values are offsetted, and they are fed to the left and the right body. So next is the singularity identification. This is obtained from the input active joint variables. If this matrix becomes 0, then there is an activated singularity. And if this is the passive variables, this is the 8x8 matrix for the entire body alone. So there are, as you can see that there are 4 actuators, and there are totally 8 equations considering the scalar form which was mentioned earlier. The K star is the matrix which denotes the passive joint variables, and if this is 0, that means that the robo is in a singularity position. And this is a singularity condition where the theta 1 plus theta 2, sine of theta 2 plus theta 3 becomes 0. If it is in this condition, the robotic lizard, previously we saw it as a triangle, it becomes like this, then it gets confused whether this goes down or up. So this condition should not be met, and this parameter has to be taken into consideration while designing the control system. And this is for the subsystem 2, that is the leg, and the conditions for active and passive are shown in K and K star matrices, and it can be easily formed that in equation at the bottom. If the condition is at 0 degree or 180 degree, the entire mechanism would come to a singularity point. So gate analysis. Gate, we haven't focused much on gate analysis in this work. We have just did a literature survey and tried to implement the walking and the trotting gate on the robotic lizard. And this is the CAD model of it on the top, and at the bottom is the 3D printed model. And this is the walking on a straight line, and another is the thing, it is taking a turn. And coming to the conclusion, we presented a robo which actually mimics a gecko. We optimally designed it so that it can the link lengths are optimal. Then the dimensional synthesis, kinematic analysis, and the singularity identifications were done. It closely resembles a robotic lizard, and a good conditioning workspace will be considered in the future works. and then our future work will be like I will be able to climb walls and ceilings, and I'll be showing a video. Excuse me. Please stay there. This is the experimental results in the video. So the robotic lizard will be shown now. So here the leg is very much higher in the air. In the future works we will be bringing the distance between the body and the base a little bit down. This is moving on a straight line. This is all fully open loop control. There is no sensors or anything used. This is just to verify that the mechanism is working. So it's moving on a straight line, and next I'll be showing it to taking a turn towards the left. That's it from my side. I'll be happy to take this.
So, what are the practical uses of it? You're biomimicking a gecko.
Yeah.
So, I mean, what is the scope? I mean, why you have thought of this idea, and what are the practical implications? Nowadays, research is being done where it is being asked what is the use to the society of such a device?
Yeah. The practical use of it is the thought which I have in mind is it is for the soldiers. The soldiers can carry a lizard, or not this version of course. They can carry a lizard which resembles a real robotic lizard which resembles a real lizard, and they can make it climb inside the caves and find out whether anyone is hiding in the cave, and they may not be aware whether it is a real lizard or a robotic lizard. So it can be used for surveillance purposes.
Yeah, I have one question that in case of this rotary motion as well as transitory motion that you are showing, I wanted to know that how you have incorporated this, because you have to change this sequentially. You have to program that where to friction will be working, and at which point friction should be withdrawn from the ground. Ground friction should be, that means this leg should be attached to the ground at a certain point of time, and it should be detached. Yeah. Another leg should be detached at a certain point of time. At the same time, so there is a typical sequence of operation, yeah, of touching and detaching. Yeah. So how you have incorporated that in your logic?
So there are actually 8 sequences, 8 angles with us in hand, 2 for each leg, 8 positions for each leg. So there is a delay given in the Arduino program when we programmed it. So it follows a sequence. The 4 angles are given, it makes a step, and then there's a delay for 1 second, and then there is a other 4 angles where it has to reach, it is given, and then again there's a delay for 1 second, and the loop continues like that. So this is like we followed a paper which we have cited in the our own paper, where we took the gait diagram. There's something called as a gait diagram for a lizard, actually, for how the lizards walk. There's a black patch which comes like this in a cross manner. So within that we need to maintain the time, and we have to program it accordingly.
But what is the amount of friction? How you are controlling
it? It is like
that method which you are telling. That is only this friction is affected because of its own weight.
Yeah.
If equal to mu into A.
Yeah.
Okay. If weight is increased, that means you are not giving any actuation, so it is having some friction because of its own weight.
Yeah.
Now suppose if I am going to such that you are telling one example of cave, Yeah, because in that case you may have to move the lizard in the ceiling also, in the vertical wall also.
Yeah.
Then you have to devise some kind of mechanism, some adhesion mechanism. Okay. So that have you thought of? Can you throw some light?
There are adhesives which are available in the market, which can be used. Those are called photosilica.
Market different.
What Professor is pointing out is that ground reactions, ground friction, you are not.
Yeah, we have it improved. Yeah.
And that needs to be thought of.
Yeah.
Other than that, there are dynamic parameters.
Yeah.
Like the weight of the individual links and other aspects, which is still to become when you make a real kind of model.
Yeah.
This is from a kinematic perspective.
Yeah.
But from a dynamics perspective, I think a lot of work needs to be done in terms of joints, and it is sequential in the operation. And only one input and then it goes into that. So if there are independent inputs from each of the leg and kind of thing, so that has needs to be that is not been incorporated as of now.
Yeah.
The model is one input only.
Yeah. Okay.
Another thing which I was looking at, good work, no doubt detailed work. But you see in the nature you will find the motions are very smooth.
Yes.
What you are getting is jerky motion.
Okay.
So why we are getting it, that needs to be thought of. I mean, these are the actuators which we are using, the linear actuators and the rotary actuators. So instead of lower pair, can we go for higher pair mechanisms and something like that, so that you will be able to get smooth motion. That will further extend the workload. Whatever you have done, it is commendable, no doubt about it.
No.
But these are some thoughts which you can have. Anyway, Professor Anand Suresh work or ISC's work, I have seen the PG level. This was during your PhD or PG?
No, this was doing my RA.
So I have seen the work, and the volume is really appreciated.
Yeah.
I really appreciate it. Thank you.
I have a question. So what is the function of the tail? Is it a stabilizer in the gate, or because I find it moving during the gate, and also the head? So it is tilting with every step.
So we simulated the center of mass. We simulated in the Python program we wrote. So when the when the presence of tail, the motion we get is little higher, the swing.
Otherwise, it cannot be gecko. So it's modeling gecko also. It has to be a gecko kind of thing.
So the tail plays
Is it
a
just a
role.
quadruped motion, or is it really helping in assisting in the gate?
Technically speaking, it is playing some role.
It's playing a role. Some role.
And other question is there lift off in the leg, like sir pointed out, or it is just dragging along the?
It is lifting off a little, not much, a few millimeters.
And have you mounted any ground sensors or?
Nothing. We have no sensors.
Okay. So I think the kinematic configuration they have achieved through this work, but what kind of by modeling the gecko bow part of it, and you have utilized the overall lengths, and they have made some constraints.
Yeah.
So what are the parameters you have chosen to have those constraints? On what basis you have decided those constraints?
Which constraint?
You have made some lengths, link lengths and other aspects. So
Yeah.
you have just assumed that it will be at the distance between these two, it will be how much and all that things.
So we actually measured the gecko. We had papers which had measurements of the gecko's head and other things. We set the base parameters from that, and from there we went into the optimal kinematic analysis. For dimensional synthesis we did.
So it is proportional to what the length actually a gecko has. Something like that, or it is
Only one parameter we took it from that, and from that we only minimum parameters we took from that, and we formed our other parameters based out of that.
Thank you.
Thanks, sir.
Next speaker, paper ID